Good afternoon to all. Again, I am starting my presentation. This is session 2. Previous day we have discussed about the electromagnetic levitation and of a spherical object, and we have discussed many things, the coil design, how to do electromagnetic analysis, then modeling, stability analysis, fabrication, etc. for the spherical object. So already we told you that as the spherical object is symmetric object, so only one center is its equilibrium point, so it's a very easier with comparative to the asymmetric object. So in this setup you can see that the one second. Okay, you can see that the frame is steel frame, such that it can get a closed path. Now we discussed about second. Yes, now we discussed about the levitation of a rectangular steel plate. Here you can see that for the spherical object the only z direction control is required, but for this rectangular plate, x direction, y direction control is also required. So we have both higher LED phototransistor pairs, and below of this object there have one inductive proximity sensor, so it's a 3-degree freedom of control. So as the object is C type, so a C type core is used for of the coil. So coil design is a dependent on the spherical object. So as the shape is C type, so core is C type, and the number of turns, current rating, etc. will be decided on the shape of the object, levitated object. And you can see that the frame is aluminum made, so non-magnetic material, such that outside flux cannot enter in the system and cannot make the system unstable. So this type of safety precautions has been taken care of for these setups. So this setup is fixed for the rectangular plate objects. So if the shape is changed or mass is changed, so another setups will have to fabricate. So this plate is fixed for this rectangular for this prototype. Now we have discussed that if flat plate, the shape of the object is changed, suppose flat C. So when flat, if the mass is same but flat, we have changed the shape from flat to C, then whole the coil design will be changed, because the flux patterns will be changed. So flux leakage flux will be more for the flat object, less for the C type object. So everything, the flux leakage will be flux patterns will be changed. Accordingly the inductance profiles will be changed, accordingly the force air gap profile will be changed, then current air gap profiles, so all the parameters will be changed. When all the parameters is changed, then obviously the modeling will be changed, and modeling, stability analysis, controller design, different controller is required for that. So now I can go for the next slide. Okay, next one things I can say you that uh, here you can see that four, I already discussed this, that four steel plates are placed on a aluminum made platform, or so four plates are placed, and so whole platform will be levitated. And from that point of view, we need four independent controllers. So say four RLD proximity sensor pair, independent means four independent say feedback is required, four independent controller is required, four independent sensor is, everything is four actually, because the on the platform there are four steel plates are placed, and whole body will be levitated. You can see there is that we have used Small signal model means at a particular operating point the plate will be levitated. So for that for that small signal model the controller has been designed, and for that controller you can see that we have designed analog controllers. We have not done in digital platform yet. So you can see that the Pero boards we have made these circuits, and there are lots of ports because for at the last step we need to require for fine tuning of the controller. So that's here. One more thing we have added, they have a buck converter because when the platform is suppose weight of the platform is more, then we require more current, and for that purpose we need the buck converter. Current requirement is more, so the duty ratio control we are doing here. So for the problem is here that four steel plates are there. So all the air gap variations of each coil should be equal. Means no air gap variation, no air gap difference, no weight distribution, and no inductance variations should be there. So spirit level accuracy for the platform and for the coil and for the object is required, and then we can go for the modeling, parameter evaluation, stability analysis, etc. Now one things I want to show you that when we are trying to design the to implement the controller in Pero board. Actually, what happens that electrical disturbances can arise from the Vero board. So, electromagnetic levitation is very much sensitive. Small amount of electrical disturbances or mechanical disturbances can immediately make the system unstable. So, they are have required to make the system the system robust. So for that point of view, PCB is the most sophisticated way to avoid these disturbances. So you can see here that the PCB is using, so there are lots of ICs and power supply you can see. Now we can do. So first point, that is that where is the application. So already I told you that electromagnetic transportation and magnetic bearing, induction melting, there we can use. Okay, now you see this is a small LIM, linear induction motor. If we can levitate this object, so it can become a small type of kind of prototype of maglev vehicle, because this will work as a propulsion. This linear induction motor will work as a propulsion, and if at the same time if we can levitate it, then it will be a maglev vehicle. So the line track is also a very important aspect, because track nowadays superconducting magnets is using in the track, so track is so costly in maglev vehicle. uh, Now I can go to the main slide. So previous day we discussed on the levitation of spherical object of 62 gram, and discuss also C-shaped plate of mass 148 gram and flat plate. Uh, so we are going to the flat and C type object. Uh, yes, this we discussed analytical modeling. Yes, sure. Here one things you can see, this prototype, uh, these prototypes is uh, this prototype is first you will have to make it in AutoCAD. So for spirit level accuracy and true mechanical zero setup, AutoCAD drawing is important. From AutoCAD drawing we can go for the manufacturing, and that manufacturing will be at professional manufacturer, just like MSME tool room. So I discussed this for the steel plate, and now I can show you that inductance plot at, because this is a flat plate, so x direction y direction is also important. Now in x direction we can see the inductance variations. So displacement in x direction, and we can plot the inductance. And similar way, z is fixed, we can draw lx, and x is fixed, we can draw lz. So different way. So we can match this experimental, analytical and simulation value all are almost same. Then different parameters. So we are discussing for the flat object of 148 gram. Now we can plot the different type of parameters. So force constant, force air gap plots, current air gap plot, etc., and force air gap profile. So force is dependent on the inductance. Okay, inductance is dependent with the current. And now when if we get all the parameters, then we can go for the modeling. Okay, before that, before going to the modeling, this type of parameters evaluation is important, because now we are working in 3 degree control. So for 3 degree control we require the parameters in not only in the z direction, just like spherical objects we evaluated parameters in z direction, different parameters, current air gap, force air gap, inductance air gap in z direction. Now we'll have to check parameters not only in z direction but also in x direction and y direction also. In x direction, what is the behavior of the uh, inductance profile, force constants, etc. And one interesting thing is that in x direction, for the flat object, when we checked the inductance at x direction, we find out there have one restoring force. Means if you give a disturbance in x direction or y direction, necessarily it will come at the operating point. Means it at a certain level it will not make the system unstable. There have actually limitation. So within limitation, if you give disturbance, then automatically it will recover, it will come at the operating point, it will not become unstable. But with before uh, out of the limitation, if you give disturbance, then it will goes away from the operating point. So natural restoring force is exist here. So point is that already I told you that there are requirement of x direction and y direction control, but here we have found that they are having one natural restoring force. So it can decrease our effort very much, because that we can come in a point that if we don't use so x direction y direction control, then also the system will become stable. That is the advantages of restoring force. It exists in levitation. So this create this will help us actually. But if we add additional x direction y direction controller, then that will be the stability will be more, stability will be better. That's the advantage. Now if x direction displacement, we can plot different parameters of the restoring force. So restoring force plots are shown. It is in through FEM analysis, and these are the analytical uh, model. This from the analytic. So same way, like spherical object, we can design the coil parameters. So coil current rating is 2 ampere air, number of turns 1000, area of core, length stack, turns per layer, number of layer, width of stack, wire gauge, etc. So when the object is fixed, suppose 148 gram, and the shape is fixed, suppose C type object. Now we'll have to do the electromagnetic analysis through FEM softwares, and from that we will get the idea that what should be the current rating of the coil, what should be the number of turns of the coil, because there should be a good relationship. Already I told you that coil and the object, there should be a good relationship, otherwise the system, to make the system will be very difficult. So once the coil design is ready, because coil how much current is required, that is dependent on the uh, weight of the object. From the weight of the object we will have to design the current rating, etc. of the coil. That so to get a clear idea about that, we need to do FEM analysis, and from that we can design the coil. Once coil design is completed, then we add the operating point, so from where operating point is coming, from the inductance profile. From the inductance profile we will have to choose the operating point. Please see inductance profile. Where is the inductance profile now? Yeah, that is it. From figure 37, please see that when the coil is going from 10 mm to touch the coil, then the at the when it is going to touch the coil, then the inductance is, sorry, it is force erg profile. So inductance profile is this. Yeah. Figure 33, you can see that when the object touches the coil, then inductance is high. When it away from the coil, then inductance is inversely decreasing. And you can see at 8 to 10 millimeter almost constant, and at 10 millimeter or 15 millimeter or 20 millimeter, the inductance is constant, and that is the coil inductance actually. So after 10 millimeter, there will be no effect of the coil current, so it will give the a fixed coil inductance, so there will be no effect actually, but there will be inductance that is due to the coil. So coil inductance. Now we can move to the okay, yes, yeah, this is the coil specification. So coil specification is not a very easy task actually. You can see that required force is 1.48 newton, that is the coil force, because we will have to nullify the weight of the object, then only it will be levitated. So coil force will be equal to the mc, then it will become step. So we require this force 1.48 newton, that is the mc. We will have to generate this force through coil, and for that, for to generate this force through coil, this is the coil parameters: number of turns 1000, current rating 2 ampere, area of stack, length of the stack, width of the stack, number of stack, wire gauge, current density, area of the gauge, diameter, area of coil, length of the number of turns per layer, number of layer. So this overall coil design is important. Okay, this coil wheel is the actuator, and this coil will levitate the object. So current will pass through this coil. So there should be a good relationship between the object and the coil. So the weight of the object was 1.48 newton, means 148 gram into 9.8, 1.48 newton. Accordingly, the coil has been designed, and operating point has been chosen at the from the inductance profile, where there have constant the inductance profile almost constant, and from that we do choose the operating point such that it will help in modeling. So when the gap is very small, at that point if we choose the operating point, so stability would be very difficult for that. Okay, now we have same way for the spherical object, we have linearized the model, and here you can see that the, so already I told one force is in upward direction, one force is in downward direction, and they have a acceleration. And before linearizing the model, the equation was non-linear, because there was one term force that was highly non-linear, and we have linearized the model at particular operating point. Particular operating point has been chosen from the inductance profile. From the inductance profile, we have got idea that at that point the possible levitation is possible. Levitation is possible actually. All the points in all the points levitation may not be possible. So where there have a constant curve, from that point we took the operating point. At that operating point we have taken all the parameters value, and that parameters value have been put on the equation, and then we have got the second order transfer function del z s by del is. So in the mechanical dynamics, the output is position and input is current, and coil is also electrical dynamics. So coil, in the coil there have the output is current and input is voltage. So for coil the input is voltage, output is current, and mechanical system current is input and position is the output. So final output is position. So we are sensing the position and sending it through the feedback and then through controller, and then it is in the RL circuit, the coil voltage is the input, current is the output, and in the mechanical system current is the input, position is the output. So overall system is a third order system, and mechanical dynamics, they have one unstable pole at 14.5. So now you can see that the closed loop system, the frequency response of the closed loop system. Now controller has been designed through MATLAB or simulation softwares. Now you can see, check this frequency response plot of the overall closed loop system. Gain margin infinity, phase margin 55 degree. In the same way for here root locus of the overall closed loop system, and this is the root locus of the overall closed loop system at gain 6 flat levitation. So same plot we have shown. So this is the block diagram. You can see that levitation object here. You can see this is the levitation, this is the mechanical dynamics, okay, and this is the electrical dynamics. This is the mechanical dynamics. Okay, so in electrical dynamics you can see del V is the input, del I is the output, and in mechanical dynamics del I is the input, del Z is the output. So this is the overall system where there are mechanical part and electrical part, so electromechanical system. Now two loop controller is used here. One is current controller, this is the current controller, and one is position controller. Okay, so inside you can see that you can see this is the current controller. Okay, this is the current controller, and they have outer loop, they have the position controller, and in the current controller they have one PI controller. Okay, you can see here that this is the PI controller. This is the PI controller. This is the PI controller. And outer loop there have the lead compensator. Outer loop there have the lead compensator. So inside there have a PI controller, and outer loop there have the lead compensator. But all things you must remember that inner loop the should be faster than the outer loop. So frequency of the inner loop should be faster than the outer loop, because inner loop will finally give the output to the finally act as the actuator. So actuator is the inner loop. In inner loop there have the actuator, so inner loop should be faster than the outer loop. So and feedback gain is the 1000. This feedback gain actually the weighted gain combination of approach. From weighted gain of gain combination of approach we have got this gain. So position is the output, so this gain is voltage per millimeter. So so position reference voltage. So position reference, so this is the reference voltage with respect to position. Now the error will be generated here, and then lead compensator will act, that is the outer loop, and then it will go to the inner loop. Inner loop there have the PI controller. So two loop controller is here, and feedback gain is 3 because current sensor we are using, so feedback is 3, that low. And now question is that once we get this controller in MATLAB, where phase margin is 60 degree, gain margin is phase margin is 30 degree, gain margin is 60 dB. So we have observed this controller is the perfect for this system. Now we'll have to implement it in practically analog controllers. So you can see there are lots of op-amps. Yeah, so I am discussing this. Okay, you can see this is the okay, excellent. You can see that this is the differential subtractor actually. So and this is the buffer, first of and second of, and these two are buffers. So this is differential subtractor, and this is uh, this is the lead compensator after. Okay, this is the, if you calculate the transfer function, so the same transfer function will come according to the design. And this is the second subtractor, means inner loop subtractor, and this is the PI controller, and these two are feedback. Okay, so same block diagram. So from MATLAB we have designed the controller, and we have checked all the gain margin, phase margin according to our stability criteria, and then the system has become stable. Now we'll have to implement it analog platform. We'll have to implement it practically. So this is the op-amp based circuits, analog circuits. And if you check the transfer function, suppose 4 into s plus 45 by s plus 450 is the transfer function of lead compensators. So if you check the transfer function and in back calculation, you will get that transfer function 4 into s plus 45 by s plus 450. So lots of non-inverting and inverting amplifiers have been used, and so we are working on the analog platform. So same, and here you can see that there have a 1000 feedback in outer loop. So here also you will get the thousand feedback. So non-inverting amplifier has been used. Now now final uh, driving circuit is the transistor actually. uh, so we will driving circuit of the coil is transistor. So transistor is operating as a linear amplifier. So which one is controlling the current of the coil? Transistor. So transistor should be at operating point. Operating point means that at operating gap, which is the operating current is required, that current should be provided by the transistors actually. So transistor is operating as linear amplifier in this circuit. So you can see this q point, q point. So these q points, the red q point, this is the operating current, this is the operating point. So we'll have to force the transistor to stay at this current. Means finally we are controlling the current of the coil through a transistor. So transistor should give a fixed current 0.9 ampere at stable position. Okay, now we can see the waveforms. Here you can see that this is a steady state response, this is a transient response. This steady state response, there you can see that 50 hertz ripple is there, and in transient response you can see that small overshoot is there. Okay, now I can go to the practical setup. You can see that during stable levitated position we have taken this snapshot, figure 52, where flat rectangular plate is being levitated, and this is the prototype. So what we can come to conclusion is that for the spherical object, center of mass is equilibrium point, so spherical symmetry, and for rectangular object the shape is asymmetric. So when shape is changed, so lots of things has changed. uh, for the spherical object we require only z direction control. For the flat object we require x direction control, y direction control. For the spherical object we require ldr and light bulb as a feedback sensing. For the flat plate we require led phototransistor, inductive proximity sensor, etc. For the spherical object we require I type core. For the flat plate we require C type core. For the spherical object we require the levitation frame should be steel such that it get a closed path. For the flat object we don't require this, because C type core and flat objects automatically it will get a closed path. So, and for the flat plate we can see that there have a lots of leakage flux. For the flat plate there have leakage flux is less, but still the to levitate a spherical object is easier than to levitate a flat plate, because for a flat plate x direction y direction control is not required, but for flat plate we require x direction control, y direction control, and we'll have to consider roll PCO, etc. So this type of differentiation is there when shape is changed. So when shape is changed, coil design is changed, whole the prototypes is changed, and modeling changed, analysis is changed, more source controller is changed. In spherical object we observed only one loop, but for the flat plate plate, we have seen that two loop control is required. One is for mechanical dynamics outer loop, and one is current control loop, inner loop. So this type of, and for the flat plate, and we have seen that C-type core is required, and for the spherical object you can see that the coil is big. Okay, coil is big compared to the object. Because of that, it is not getting closed path, so leakage flux is more. Obviously, current rating of the coil is 1 ampere for the spherical object it was, and for the for figure 57, the current rating of the coil was 2 ampere. Okay, so dimension is also important, because dimension for to design a electromagnetic levitation prototype, we need to design the prototype in AutoCAD. Okay, main and prototype, main setup or main frame, we can say, that should be drawn in the AutoCAD. And also it will help in analysis also, because in ANSYS simulations it can directly import the AutoCAD drawing, so this will help. And then because spirit level accuracy and true mechanical zero setup we required. Okay, so I told you that true mechanical zero setup is required, because the flux from the outside cannot make the system disturb, or cannot hamper in the system stability. So at spirit level accuracy, because we are working against the gravitational force, so we require to place the object at spirit level with respect to the surface of the earth, and the core also at spirit level, such that there have no air gap variations at all the points, and there have no weight distribution variation, and there have no inductance variations. So actually one is dependent on the another. When induct, there will be no air gap variations, there have no inductance variations, and when there have no inductance variations, there have no weight distribution variations. So this one is related with the other. So this is also important. The 3D model is also important, because from 3D model analysis will be done, and from 3D model the fabrications will be done by the experts. So this is important. So you can see, okay, now you can see that FEM analysis is also important, electromagnetic analysis, because when we are going to design a electromagnetic prototype, first we have the object. First we have chosen a particular weight of a spherical object or rectangular object. Then we know the weight of the object, shape of the object is fixed. Now we have designed the coil, but from where we will start the coil design? For that we require the electromagnetic analysis. From electromagnetic analysis we will get the idea that how for this amount of force, levitated force means the object, weight of the object, because this weight of the object we will have to levitate. This weight of the object will have to balance by the coil. So for to balance this weight, we require this amount of force through the coil. So for this amount of force we require how much number of turns, what should be the current rating, what should be the wear gauge, etc. will come then. So from the weight, means from the weight it is coming that this amount of force we require at this point, at this operating point we require this amount of force by this coil. So once this is fixed, then coil design will start. For this force I require this number of turns, this number of wear gauge, this number of current rating, this and this. So electromagnetic analysis is important. So figure 58 you can see there are lots of leakage fluxes, and figure 59 there are a blaze leakage fluxes because it is getting a closed path. You can see here, you can see, okay, you can see this is the straight line, all are straight line, entering, exiting, yeah, okay, from the core, and then it is passing through this and this, it is entering this. So this way it is closed path, so leakage flux is very less. But in this case spherical object case, please see that flux is entering, exiting, then passing through this and this, okay, this, sorry, this and this, okay, by this way. One second, you can see that flux is entering into exiting from this and passing through the ball, and then again this by this way and by this way. Few flux are going by this way, flux is this way, and then it is a closed path, okay. Okay, so you can see this flux is going by this way, few fluxes is going by this way, then it is a closed path, and few fluxes are going this way, few fluxes by this way, then this is a closed path, and now this is also a path by this way, okay. But in this case you can see the state it is coming by this way, this way, this way, so closed path. So you can see that we have to make the frame is also steel such that it can get a closed path for the spherical object, but for the rectangular object we have no require of uh, of a steel frame because it is already getting a closed path, no need of external support, okay. Now we have to fabricate of the electromagnetic limitation prototypes. That is a very important part because a true mechanical zero spirit level accuracy is required in the setup, and then it is when it is done and feedback sensors are aligned in the right direction, and for those you can see that a four pair of RLED phototransistor pair are used in figure number 61, and because to create a operating zone, okay, to create a operating zone we require a weighted gain combination of approach to make the system to give feedback to the controller. And but for spherical object figure 60 you can see the only z direction is control is sufficient, so we have put on an LDR and light bulb. Actually for the spherical object also IR LED phototransistor is also used in few setups, that also you can use higher LED phototransistor pair, only one direction control is sufficient. But for flat plate required there have lots of sensors because x direction, y direction and z direction all to taken care of. So 3-degree freedom control, for flat plate it is a 3-degree freedom control, and for spherical object it is a single degree of freedom control. Now I told you that for parameter evaluation and parameter uncertainty should not be there. So parameter uncertainty we'll have to avoid. So for to avoid parameter uncertainty we'll have to check the experimental waveforms, experimental parameters with simulation and analytical. So we can get the parameters through experimental as well as simulation and analytical. Analytical model is fully based on mathematics, so using Pohl's method, flux calculations, lots of integration, because we'll have to calculate the inductance. If we so how will we calculate inductance through mathematical model? We'll have to calculate the cross sectional area, okay. Because inductance is nothing but mu naught into n square a by z. Mu naught is the permeability, n square is the n is the number of turns, a is the cross sectional area of the flux line. Cross sectional area of the flux line. So that is the that a is important. A is the cross sectional area of the flux that can be calculated by integration using Pohl's method. If we can get the A, then we can easily get the inductance plot from the analytical model. And figure 63 shows for flat plate the flux line, how few flux lines are exiting from the core is straight line and few are bending. Few fluxes are bending, few fluxes are exiting from the surface of the core. So that should be that all the flux lines you'll have to calculate, and you'll have to using Pohl's method you can get the inductance profile, and that inductance profile you'll have to match with the analytical simulation and experimental. You can see from figure 64, figure 64 or you can see, okay, figure 60 there have the error between and between experimental and analytical, because analytical, what happened here that in analytical model we have considered uh, all the flux line actually, but in practical there have a lots of leakage flux that is not considered. So here there have a error. So to levitate, if we think in control system aspects, the to levitate a spherical object is easier, but to calculate to bring it in analytical model is difficult for spherical object. So to levitate or to design controller is easier for the spherical object, difficult for the flat plate, but to design analytical model is easier for the flat plate and difficult for the spherical object. Just reverse. So now we have received all the inductance plot, current error gap plot by three ways actually: analytical, experimental and simulations. So parameters evaluation is important here, because we'll have to check the parameters through experimental, analytical and simulation. There should not be any variation actually, because parameter uncertainty will force not to design model the system properly. So parameter uncertainty, if they exist, then obviously modeling will not be correct, and if modeling is not correct, then stability analysis, controller design, everything will be wrong. Ultimately the controller will not act, controller will not be able to make the system stable. So parameter from the starting point we will have to take all the precautions. So what I am trying to say, from the starting point we are trying to minimize the errors in the taking the shape, taking the object, coil designs and parameters evaluation. If we try to minimize these errors, so it will help later. But if errors are added in the starting, and if suppose our parameters evaluation is not correct, design is not correct, then obviously there are no chance to make the system stable by any kind of controller. So all the efforts will be useless. So from the starting point we will have to take precautions such that no error can come from the parameter uncertainty, no error can come from the design aspects, no error can come from the coil design aspects, and then we can assure that now we can start our modeling. If we can assure that we can start our modeling, then we can do the we can design the controllers using softwares, and then finally we can design the analog controllers in analog platform. And then also parameter uncertainty will be there. Already I told you that how we are trying to minimize the error, but still there will be some parameter uncertainty because there are few hidden parts that we are not aware actually. Then disturbance can arise from anywhere, from the circuits, from the mechanical side, from the electrical circuits. That type of parameter uncertainty will be add up, sum up at the practical results. So when we will go to the practical waveforms, then we will find out some parameters uncertainty is there, though it has been stably levitated. So these type of force air gap plots, etc., all the parameters. Now force air gap plot in simulation and practical and analytical. So analytical, so simulation easily we can get it through an ANSYS software, and but from analytical also you will get the force air gap plot, because if we can get the inductance by through integration, the cross sectional area, we will get the inductance. If we get the inductance, force is nothing but the minus half I square dl by dz, the current square into derivative of the inductance plot. So now by this way we can get the analytical force air gap plot. Practical force air gap plot also we get. Okay, how? So we will keep the object at a particular operating point, and then we will change the operating point, then we will change the operating point. By this way we will get the current, how much current is required. And once we get the current air gap profile, easily we can and get the force air gap profile, because force is nothing but the c into I by z square. So if we can get the current air gap plot practically, then we will easily get the force air gap plot practically, because current force is nothing but minus half I square dl by dz. Sorry, F equals to minus half I square dl by dz. Okay, so if we get the current air gap profile, then we will get the inductance air gap profile also practically we will get. So inductance air gap profile if we know, if we get, and current air gap profile if we get, then by formula we will get the force air gap plot practically. Simulation already we have got, analytically we have got, and simulation, analytical and practical. By this way we have to check by three way, such that parameter uncertainty don't come in the system. Now see some practical data. See that we require to levitate the object, that is the mass of the object is 0.62 gram, so 0.6 newton we require. So we'll have to levitate 0.6 newton. So when the force, the weight of the object is will be equal to the force produced by the coil equal, then it will be levitated. So spherical object is 0.6 newton, flat object is 1.45 newton is required through coil. Current rating is 2 ampere for the spherical object, current flat 2 ampere, same. Here number of turns is more, number of turns is less. You can see that here number of turns for the spherical object is more. But we need required force is 0.6 newton only it is producing. At 16 millimeter gap it is producing 0.6 newton by 3600 number of turns, and here only 1000 turns we are getting 1.45 newton. Though the air gap is different, but still I am telling, I am pointing out to the point that here leakage is more for the spherical object. So that's why we are getting the number of turns is more, but we are getting less force because leakage is more. Practical values of the system parameters: spherical object you can see that two type of differences: 62 gram, 148 gram. 60 millimeter we have chosen the operating point. For the flat plate we have chosen 8 millimeter as the operating point. Current and is this at operating point. Flat plate 0.7 ampere. Resistance is fixed. Inductance at operating point changes, and such. These parameters we required for the modeling. Now we are getting the this linearist model. We are working on the linear model. At a particular point it will be levitated, not all the points, so we are not going to the average model. So slide as for average model we will have to go for the non-linear controller, where all the points at each point we can make the system stable. So, but here only reference here we'll have to put at operating point only, so reference would be at the operating point. So mechanical system dynamics, you can see second order system, where on unstable pole is there at 14.5. And the electrical dynamics, because coil is a electrical dynamics RL circuit, so R plus L di by dt equals to V, and we get the current versus voltage here. For in the coil, the voltage is the input, current is the output, and mechanical system, current is the input, position is the output. So it's a fast order system. So electromechanical total overall it's a electromechanical system. So third order system, you can see for the spherical object there is on single loop, and for the flat plate there have two loop. On is position controller loop, and inside they have the current controller loop. Two control loop is required for the flat plate. So control strategy has been totally changed. And then the block diagram, from the block diagram you can check the body plot, root locus, etc., where you can get the idea about that how much gain margin we require, how much phase margin we require for the closed loop system, because system was unstable actually. Now the system has become stable. All the pole you can see in the left hand side. Now closed loop system poles, closed loop poles are in the all the left hand side, and gain margin is 55.2 dB and phase margin is infinity. So system has become stable. Now we can check the transient response and steady state response for the ball levitation and flat levitation. There are a few differences because here there have some overshoot, but both the cases actually they have some amount of overshoot, but system has become stable. And steady state response also, you can see that the system has absolutely stable. That ripple is coming due to the 50 Hz ripple that exists in the, though we have used SMPS switch mode power supply, still there have some fluctuations ripple in the DC. So you can check this, that a spherical object in figure 84 has been levitated, and figure 85 and flat rectangular plate has been levitated, and this is the full prototype figure 86 for flat plate, sorry, for spherical object, and figure 87 for the flat plate. So you can see figure 86, the full prototype is still made, already I told. So such that it can get a closed path. Few fluxes pass through this spherical ball, and then it will pass through the steel frame. So to bring it in a closed path, we have made the frame also steel, but for this case they have no required because steel, so C type core and C type objects, no required of frame to be steel. Okay. Now we can go, or we can do comparative study for the flat plate and C-shaped plate. Actually the coil is here same coil has been and put here, same coil design, same coil actually. Now only shape is changed, mass is keeping mass as same, but shape is changed. Mass is 148 gram for both the setup, mass of the object, levitated object. But shape is changed. When shape is changed, the flux patterns will be changed. Flux patterns is changed, the inductance profile will be changed. A force area profile will be changed. So modeling will be changed, stability analysis will be changed, controller design will be changed. Everything will be changed. So only shape is changed. Just here coil is same, mass is same, but shape is changed. So everything will be changed. You can see this. Uh, Only shape is changed. Here flat plate, here C type plate. So before going to the this, we'll have to see that the electromagnetic analysis for the setup is important, because from electromagnetic analysis we get the clear idea about the coil design. Before going to the electromagnetic analysis, we cannot design the coil. So first the shape and weight is fixed, then coil design has been done, and then we can go for the supporting frame of the prototype, and then we can start the parameter evaluation. So you can and get the parameters by different ways, simulation, analytical, practical. And then once if we get the parameters etc., then we can do the modeling by using Taylor series expansion, small signal model. And then we can go for the stability analysis, root locus plot, body plot, etc., where we have taken that system should be 30-degree phase margin, and gain margin is 60 dB. And then we can design the controller using MATLAB or other platform, and then we can design the controllers is designed, then we can go for the practical platform. So practical platform we will have to use, because we are working on the analog controllers, so we'll have to use the OPAM LM324 or TL084, and using that first we will start in breadboard and then hero board, and then after testing when it will work properly, stable levitation condition, and then we will go for the PCB, finally PCB. So now I can start this, I can end this test session, and next day we will discuss from this from here. Okay, thank you.